I tried to find a picture of photon, however, I couldn't. We see light rays everywhere. However, no one knows what exactly just one photon looks like. So we don't even have the technology to look at a photon yet because it's massless. Okay, so in theory, um, it's a particle, but actually we can't even see it. Okay, but even this, we are we are able to do some calculations on it. Okay, so since photon is a particle now, okay, for a particle, and it has a speed. Its speed is the speed of light, which is 3.0 times 10 power of 8 meters per second. Okay? And this number cannot be changed. Okay? So, and light always travel at the speed of light. There won't be any acceleration, there won't be any deceleration, and that's it. Okay? But when we're dealing with photons, okay, we're always interested at its energy. Okay, so how much energy does a photon carries? Okay, the formula to find that would be E, okay, the energy of a photon, okay, EP, okay, equals to h times its frequency. Okay, just remember the energy of its photon is related to its frequency. It's directly proportional to its frequency only. Okay, h is called the Planck's constant. Planck constant. Okay, so let's type in Planck's. Have a look. Okay, he's a scientist. He's a very really famous scientist. And my internet is down, so let's not worry about it now. Okay, uh, Planck's constant is 6.6 times 10 power of minus 34 joules seconds. Okay, don't worry about um, the units there. Okay, the units for Planck constant doesn't have any physical meaning. It's just put it in so the units of the equation between energy and frequencies are balanced. Okay. It may have a special meaning, but um, just now no one can interpret it. Okay. You can try to interpret it, but just don't worry too much about it. And notice that 6.6 times 10 power of minus 34 is a really small number, okay, because we're dealing with the energy of a single photon. So we always work with small numbers. Okay? And to make your life easier, okay, what the scientist he used uh, well, the scientist discovered a unit to actually for the calculation of energy of photon. Okay. Normally we use joules as a unit of energy. However, in this chapter, sometimes you're going to use a unit called electron volts as the energy of something. Okay. Just remember, electron volts is not a voltage, it's a unit of energy. Okay. So 1 electron volts is equals to 1.6 times 10 power of minus 19 joules. Just make sure you'll be able to calculate that. Okay, so easily we can convert Planck's constant in electron volts. Okay, so now it's 4.1 times 10 power of minus 15 electron volts seconds. Okay, this is the Planck constant if you use the unit of electron volts. The idea is this. That let me just do an example. Okay. Say if I have a frequency of let's say 5 times 10 power of 9, okay, hertz. Okay. I have something give me a frequency, give me a radiation of the frequency of this. Okay, and if I want to find the energy carried by each small photons of a radiation of that frequency, okay, what I do is I use the equation E equals to HF. Okay. Your frequency is 5 times 10 power of 9, okay, and H is Planck's constant. So if I use this number, okay, if I use this number here, 6.6 times 10 power of minus 14, then I can type it in your calculator, I get an answer, and it's in joules. I get an answer of some sort, and it tells me how many joules of energy is in a photon of that frequency. Okay. However, okay, if I use this number there, okay, 4.1 times 10 power minus 15, okay, in the equation, I will have a different number, and the unit of that number will be in electron volts. Okay. So, in order to decide which Planck's constant you want to use, it really depends on you. It depends on how you want the units to be. Do you want to measure it in joules or electron volts? Okay, now that's the basic equation of photons, the energy of a photon. Okay. Now let's do some more. Okay. Now just remember. Okay. Let me just refresh your memory first. Okay. So what's happened is we have metals. Okay. And when we shine light on it, okay, an electron will escape. Okay, that's what we talked about before. So if I use a frequency that is, so according to this equation there, according to this equation here, okay, if I use a frequency that is lower, okay, the photons will carry less energy. Okay. Thus, for some metals, okay, if I use a lower frequency, an electron would not be able to escape. Okay, and the minimum frequency of light to make electron escape on a metal are all different. Okay. It depends on metals. So it's different for iron, and it's different for gold, and it's different for silver. Okay, so what does the scientist did is they found something called the work function. Again, it has a fancy name. Now, a work function is basically the minimum energy needed in a photon. Okay, needed of a photon. Okay, in order to make an electron escape from a certain metal. Okay, so the symbol for work function is just a minimum energy. Okay, it's W or sigma, or not sigma, or this thing, Greek letter there. Okay, and it's calculated as H times F0. Okay. H is our Planck's constant. F0 is the minimum frequency. Okay. The minimum frequency that I need to supply to a certain metal, so there will be, so its electron would move away. Okay. And the minimum frequency are all different for different metals. Okay, so and this is very, yep, and this is here, this equation here is the very equation that Einstein developed, and he got a Nobel Prize for that. Yep. Okay, so I know, okay, the theory behind it is not hard. Okay, we are this week, well, in this area of study, okay, we are basically learning the cutting edge science 100 years ago, in 1908. Okay, now back then, if you be able to understand this in 1908, you're more likely a university professor or a scientist. Okay, and even some scientists were struggling to understand this concept back then in 1908. Okay, yep, and remember the equation for work function? Okay, now okay, imagine this. Okay, now let's do some more equations. Okay, so the other important equation is about the kinetic energy, the energy held in electron. So the kinetic energy in the electron. Okay, just remember that. Okay, so photons come to the metal with some sort of energy. Okay, okay, in the form of this EP. Okay, so the energy of photon, okay, yeah, coming to the metal, okay, it bombards with the electrons in the metal. If there is enough energy, okay, the electron will move out. Okay, so what's happened is the energy coming from the photon take away the minimum energy required, okay, to make an electron escape, which is the work function, will be equals to the energy left will be the kinetic energy of the electron. Okay, so this is another important equation here. Okay, so the the energy carried by photon is basically the energy input. Okay, take away the energy needed in order to make the electron escape. Okay, will be the energy left, which is the energy carried by the electron. Okay, the kinetic energy of the electron. Okay, and yep. So we can basically elaborate this equation. Okay. The energy of the photon can be measured as hf, the Planck constant, times the frequency of the light. Take away the work function, uh, basically is h f0. Okay. Remember, yep, this is the minimum energy that requires to make electron escape. Okay. And F0 is called the minimum frequency of of a metal, and it's different for different metal. Okay. And equals to the kinetic energy of the electron. Okay, just remember this formula there. Okay. Now, the other thing we need to talk about is the momentum. Okay. We will be doing a lot of work on momentum next week. Okay, but in this week you just need to know this. Okay, now since photons are particles, and every particle, actually every moving particle, they need to have a momentum. Okay, so and the momentum is calculated as mass times the velocity, but in this case the mass of a photon is 0. Okay, and this is confusing. So if the so the yeah, and this equation just does not work with the momentum of photon. Okay? Because if the photon doesn't have any momentum, photoelectric effect wouldn't happen. It's not a particle. Okay? So in order to make photon behave like particles, it must have a momentum. Otherwise, collision won't occur. Otherwise, electrons cannot be knocked out by photons. Okay, so what we have is the momentum p of a photon is equals to its energy divided by the speed, and its energy is calculated by hf, okay, divided by the speed, which is the speed of light. Okay. We can rewrite this equation in this form. Okay. Remember, speed of light is basically frequency times the wavelength. Okay. So this is how to find. Yep, this is how to find the momentum of a photon. Okay. To make it simple, is basically uh, the impact power of a photon. Okay. High frequencies of radiation are able to do you more damage, yeah, because it carries more energy and it carries more momentum.